Hello, I'm Jinju Wang. In last video, we talked about the data preparation and the data process module of Luto. So now Luto have the capability to answer the following question. Given a year between 2010 and 2100, we randomly select a pixel. We randomly select a location in Australia. So we know what is the water supply of this pixel. Is it a dry land or irrigated land? What is the land use of this pixel? Is it apple, livestock, rice with a cereal, etc.? What is the product of this pixel? The tonnage or milk it can produce? And what is the revenue and cost to produce such product? And lastly, what is the biodiversity score? And what is the water requirement for plant such trees or such crops? With all those informations in hand, we now can finally get into the solver and the simulation part of Luto. Let's open an VS Code editor, and the solvers can be found in the Luto directory and the solvers subdirectory. Before getting into solver, we need to first look at the input data. We click this input data.py file and we can see all the content within this file. The important part is in this section. In last tutorial, we talked about the Luto economics agricultural quantity submodule, which is now imported as ag quantity. In a similar way, Luto has imported all the data process into these several lines. At last, all those imported modules was used inside this solver input data class. So in one word, we have now put everything, we have processed all the data and put all the data into this class. Now let's go back to the solver module. We can see it is using some Groby solvers to do the optimization. And here, the Luto solver, this is the core of all the optimization process. Within this Luto server, we can see the first line is this. It is initializing the input data. And we can find the input data is actually a solver input data. So with this simple line, we can now input all the necessary data into the solver. In other words, the Luto server now can answer this question of giving a year between 2010 and 2100, what is the land use, product, revenue, biodiversity, etc. Following next is self.dc variable. This variable represents the demand that Luto must meet. Essentially, this is the demand of all kinds of products that Luto has to meet. At last, in this line, we created a Groby model and give it a name. We can just think of it as a name of all the equations inside the optimizer. Following next, this block is creating some empty variables. And from here, we can know what they are doing. The first is the cell usage constraints. This is the constraint that generally says that for each pixel or for each location within Australia, it must be used for something, either apple or winter cereal or livestock. So we are using this constraint to force each pixel to be used by the optimizer. Following next is the agricultural management constraints. For example, if we have a farm of 100 hectares and we want to apply some new technology on the grassland of the farm, clearly the new technology coverage should not exceed the coverage of the original grassland. This adoption limit is similar as the agricultural management constraints. Following next is the demand penalty. For example, if we want Luto to produce like 100 tonnages of meat for a given year, but it has only created like 90 tons of meat, so it will have to pay some penalty to amend the left 10 tonnage of the meat. The following several variables have the similar fashion. Like here for greenhouse emissions, it has to be less than some target. Biodiversity has to be limited by some constraints. The next block is the answers that Groovy Optimizer is giving to us. So here we set out some answers for each pixel. If this pixel is a dry land, or if this pixel is a irrigated land, or for this pixel, is it a non-agricultural land use or agricultural management land use? Anyway, this is the answer that we want Groovy to give to us. Back to our slides. Now we have used the data process module to enable the Luto server to answer those questions. Now, in the further step, we want Luto server to meet with that requirement. First is all pixels must be used, and then the agricultural management area should not exceed the area of land use it's applied on. The several following requirement is greenhouse gas and the water use should be less than the target, and the biodiversity should be larger than the target. So how exactly does Luto achieve those requirements? We will use this as an example that all pixels must be used. Back to our code, here is the first step to achieve that requirement. Here, inside this setX variable function, we have created some variables. For example, here, we loop through every agricultural land use and we loop through every cell position. Now, we give each cell a unique name. For example, this X means the variable we want to get. This is agricultural dry land of this specific land use of this specific cell. And this variable name was appended to the Groovy model. Similarly, we created another set of variables, which is agricultural irrigated cell. For each of the land use and for each of the cell, we give it a unique name. Lastly, for a non-agricultural land use, we also created the variable. It means non-agricultural land use for each cell, we give it a unique name. Back to our slide. In order to meet this requirement, we first created three variables, aka the dry land agricultural variable, the irrigated land agricultural variable, and the non-agricultural land use variable. Now let's go back to the VS Code. Inside this add cell usage constraint function, we can observe from here the agricultural dry land, irrigated land, and non-agricultural land variables has been added up to a X sum. And the key is here. We ask Groovy to force that all those three variables are added up as one. This means that for a given cell, there could be 30% of dry land or 20% of irrigated land and 50% of non-agricultural land. That means in either way, these three variables has to be 100% for each cell. So that is the mathematical expression of saying that for each pixel, it has to be used for some purpose. Back to our slide, we ask Groovy to sum up all the variables and make the sum equals to 1, which means the all pixel must be used. Similarly, let's walk through how this agricultural management should be less than a land use coverage. Let's go back to the VS Code. First, we need to set up agricultural management variables. And the key is here. For each pixel, we will give it a unique name. And the unique name is X agricultural management of dry land. Unlike the previous variable, this variable has three layers. The first is the agricultural management name. And the second is which kind of land use the agricultural management was applied on. And the third level is the specific pixel. In this way, we set up the dry land agricultural management. We also set up the irrigated agricultural management in the same way. The way to make agricultural management be less than the actual land use it's applied on is within this function. Here, we first add up the agricultural management variables of dry land and irrigated land. So we will get the total area of agricultural management. And following that is we will get the total area of the land use, agricultural land use within the same cell. Here is the key of the mathematical expression for the pixel. The agricultural management should be less than the land use it applied on. Back to our slide. For this requirement, we now confident that, for example, we have 100 hectares of grassland, and if we want to apply some agricultural management on this grassland, we can see that the management area is less than the 100 hectares. This is the tutorial for today. We explained how Groby is translating the requirements into mathematical functions. In next tutorial, we will explain some more high-level settings of the requirement.